A great day to lecturer. My name is Samuel Din Chen Kai, and today I will give a short presentation about our group assignment for the simulation of electronic circuit application for the task 1. In my content, they will consist of 4 elements for my part, which is introduction, manual and calculation, simulation when R2 equal to 1 kilo ohm, and simulation when R2 equal to 2 kilo ohm. For the introduction, wave bridge oscillator is a harmonic oscillator that will generate sine waveform under a range of hertz, and the Wien bridge oscillator will consist of 1 amplifier, 4 resistors, and 2 capacitors, and 2 of the resistors will combine with 1 amplifier and form the output part, which is the voltage gain, and 2 resistors and 2 capacitors will form the feedback network, which is the beta, and the equation of the resonant frequency is F equal to 1 over 2 pi RC, and the beta always equal to 1 over 3, and the voltage gain A must be greater than 3 in order to begin the oscillation. According to Barkhausen criteria, there are 2 conditions that must be fulfilled so that the waveform can always be sustainable, which are A times beta should equal to 1, and the phase angle of the loop gain must be 0 at the oscillation frequency. For the manual calculation, the equation of beta equal to 1 over 3 plus j times omega RC minus 1 over omega RC. For the imaginary part, it should always equal to 0, because at this moment, the phase shift is equal to 0. Therefore, we will get that omega RC minus 1 over omega RC equal to 0. After some arrangement, we will get the final equation of the frequency is equal to 1 over 2 pi RC. By substitute R equal to 3.3 kilo ohm and C equal to 0.1 mil, we will finally get the frequency equal to 482.29 Hz. By using the equation A equal to 1 plus R2 over R1, we will finally get the table at the left hand side. And below is a simulation circuit that using the software MultiSim. For the simulation when R2 equal to 1 kilo ohm, we will get the result as a figure at the left hand side. The voltage detected is negative 424.11 mil voltage, which is almost equal to 0. Therefore, the oscillation frequency is 0 because there is no oscillation will occur. It is because when the R2 is equal to 1 kilo ohm, the gain is equal to 2. Therefore, A times B is not equal to 1 and not able to begin the oscillation because not fulfill the Barkhausen criteria. And the oscillation will only begin when the A is greater than 3. For the simulation where R2 is equal to 2 kilo ohm, the voltage detector is equal to negative 354.57 mil voltage, which is also almost equal to 0. Therefore, no complete oscillation will be formed on the graph, and the oscillation frequency is also equal to 0. It is because the gain is equal to 3 when the R2 is equal to 2 kilo ohm. When gain is equal to 3, it is able to sustain the oscillation, but it is not able to begin the oscillation. Based on the theory to begin the oscillation, the gain must be greater than 3. Therefore, the result for the R2 is equal to 1 kilo ohm and 2 kilo ohm is the same, which they will not produce any oscillation in the graph. And thank you for lending me your time to listen for my explanation. Thank you very much.
Hello, my name is Wenchen. So I'm going to continue to explain about the output waveform when R2 is increased to 3 kilo ohms and then decreased to 2 kilo ohms and 1 kilo ohms again. So first we see the graph of output voltage when the R2 is 3 kilo ohms. We can see that the amplitude of voltage output is increased to about 13 volts and the time taken for one oscillation is 2.383 milliseconds. When we click on the graph, we can see that. So the frequency calculated is 419.639 Hz. The wave is saturated at the amplitude. In the graph, we can see that. This is because the op-amp cannot produce more output than the input supply voltage, which is the plus minus 15 volts. Thus, this resulting a clipping waveform like this. Theoretically, the maximum saturation voltage is the input voltage, which is the plus minus 15 volts, but in this simulation, the maximum output voltage is only about 13 volts, so we deduce that this simulator is taking the real-life error into account, such as the leakage during the transfer process. Next, we decrease the resistance of R2 from 3 kiloohms to 2 kiloohms. When the resistance of R2 is 2 kiloohms, the gain A is 3, which is the ideal value of gain, where the oscillation will be sustained, but this is not happening in this simulation. The voltage output will be decreased to 9.9815 volt in a short time and then drop to 0 after a long time of oscillation. It's about 10 minutes I waited there, so it takes more than 10 minutes to drop to 0. This is so much different from the theory, because the theory said that when the gain is equal to 3, which is the R2 is equals to 2 kiloohms, the oscillation should be sustained. So we can again deduce that this simulation software is taking real-life error, such as the inaccuracy in the wire, resistor, or amplifier, into account. In this case, when R equals to 2 kiloohms, the one complete cycles takes almost 2.08 milliseconds, and the oscillation frequency is 480.769 Hz, which is very close to the manual calculation we did before this. After that, the resistance of R2 is decreased from 2 kiloohms to 1 kiloohms. We can see that the wave is quickly become 0 from the graph. This is because the gain A is less than 3 when the resistance R2 is 1 kiloohm. So the wave cannot sustain and no any complete cycle can be formed, whether it is theoretical or practical. Lastly, in conclusions, the oscillations will only occur when gain A is greater than or equal to 3. To start the oscillation, gain A must be greater than 3. The oscillation will sustain if the gain is 3 or little higher than 3. When the gain exceeds a large value than 3 or lower than 3, the oscillation will be underdamped and not sustained. The value of gain depends on the resistance R2 and R1. R2 must be twice or more than R1 to obtain gain of larger than 3. The oscillation's frequency calculated manually is 482.29 Hz, while in the simulation is 480.769 Hz, which is very close. The small difference may be due to the error in the simulator. In fact, error will also occur in reality because of the inaccurate resistor or in the connecting wires. So that's all from my part. I'll pass to my friend Hairi and Salsabila to explain about part task 2. Thank you.
For the task 2, me, myself, Muhammad Hairi bin Muhammad Sobri and Nur Salsabila will be present about task 2 given. For the multivibrator, what is multivibrator? A multivibrator is an electronic circuit used to implement a different of simple two-state device like timers, flip-flops, and realization oscillators. There are 3 types of multivibrator circuit, which are astable multivibrator, monostable multivibrator, and bistable multivibrator. Next, a stable multivibrator or free-running realization oscillator is another name for it. It has no stable state but only 2 quasi-stable states between, which is oscillate continually without external excitation when one transistor is turned on while the another remains off. At the same time, neither will be in the same state. In this task 2, we use 5 questions, that is TH, TL, T. T is the time taken, total time taken. then frequency and duty cycle. Next, we move to the result and simulation. This is our circuit that we build in multisim to stimulate. To build this circuit, we need an oscilloscope, resistor, potentiometer, capacitor, ground, IC555, IC4017, source and the LED. After that, we run the system in the multisim. After a few seconds, we can see a result of the waveform at the point A that being shown in oscilloscope. In this slide, we can see the result of waveform at point A at the certain of the value of RF. By using the equation that we have mentioned before, we can calculate the TH, TL, total time required, the frequency and duty cycle. For the 0 ohm, we can see that TH is 69.3 millisecond, but the TL is 0. We can see from the waveform that we have only the TH. TL we don't have. And then we move to the 1 mega ohm. We can see that the TH will be more bigger and the TL have the value but less than TH. Other than that, you can see that when the value of the ohm increase from the 0 to 1 mega ohm, you can see that the frequency and the duty cycle will be decreased. For the 0 ohm, you can see the frequency is 14 Hz and the duty cycle is 100%. While at the 1 mega ohm, the frequency is 0.69 Hz and the duty cycle is 52.8%. I will pass this presentation to Salsabila.
Thank you, Khairi, for the explanation. Let me continue the presentation. A potentiometer at the lowest level. The 7 LEDs will all light up and flicker at the same time when the potentiometer is set to 0, which means at the lowest setting. TH will be 0.693C multiplied by R1 plus RF, where C is 1F, R1 is 100K, and RF is 0. Because of RF is 0, TL is 0 milliseconds, which fits the equation TL 0.693C multiplied by RF. The frequency is set to 40 Hz and the duty cycle is set to 100%. Second, potentiometer at the middle range. The LEDs blink often when the potentiometer is set to 400K, which is in the middle of the range. Increasing the pulse rate to 346.5 milliseconds. The TL is 277.2 milliseconds when the RF is 400K. However, the duty cycle and frequency have been decreased to 55.6% and 1.60 Hz respectively. As can be observed from the waveform graph, the pulse wave for TH will be longer than for TL. Lastly, potentiometer at the maximum range. By increasing the RF value to 1 mega maximum, the 7 LEDs will keep flickering and brightening. According to the estimates, the TH and TL as well as the value of the potentiometer will continue to climb. The frequency has been decreased to 0.69 Hz, and the duty cycle has been reduced to 52.8%. Waveform will rise whereas the TH and TL level will grow. The value of TH and TL will grow when the potentiometer value is increased, but the duty cycle and frequency will drop, resulting in a square wave. Following that, multisim simulation software is used to model and test the configurable running LEDs. ratios, waveform, oscillation, and LED brightness. Modify the RF value to extract the values of T phase, TL, duty cycle, and frequency from the square waveform equated by the multisync tool. Regenerative switching circuits such as stable vibrators are the most popular type of transition oscillator because they provide a steady square wave output waveform while being simple, reliable, and easy to manufacture. Unstable multivibrators are a form of relaxation oscillator commonly employed as a regenerative switching circuit in industry. This is due to the fact that it produces a consistent square wave output waveform while being dependable, simple to construct, and easy to operate. That's all from our group. Thank you.